Okay, so this is the last section in Chapter 8 that we need to cover, 8.3, and we're talking about inverse trigonometric functions. My personal take is that this section feels a little out of place in this chapter. It's an extremely important topic, we need to talk about it, but it just feels like it belongs to a different chapter, just because Chapter 8 has been focused pretty much on graphing exclusively. And even though we are going to look at a lot of graphs at the beginning of this section, you're not really going to be doing any actual graphing in the homework for this section. We're going to be doing something that feels very different. But regardless of where it belongs, it's what we're talking about. So I want to spend the beginning of this lecture doing a review of inverse functions. This is a topic that you talk about in intermediate algebra. It's extremely, extremely important in all levels of math beyond that. I'm guessing that some review is going to help with what we're going to be covering today. So what is an inverse function? Well, we know all about functions. You've been dealing with functions for a long time now. And an inverse function is a function that will undo what the original function did. And it's a very non-mathematical way of defining that. So to give you more of a concrete example, consider this function, f of x equals x cubed. Its inverse function is the cube root function. And the reason for that is because a cube root will undo what a cube does. So if I take a number, like the number 2, for example, and I cube that number, that gives me a different number, 8 in this example. If I then take that new number and cube root that, the cube root of 8, for example, is 2. It takes me back to where I started, basically undoing what this function did. So in more precise mathematical notation, a way of saying that is if I called f of x, x cubed, and then f inverse of x, this little negative 1 up here is not an exponent, it's just a symbol used to denote an inverse of a function. But if f inverse of x is the cube root of x, then if I take the composition of those two functions, f inverse of f of x, what is this? Well, f of x is equal to x cubed, so I could swap the f of x out for an x cubed here. But then what is f inverse of x cubed? Well, f inverse is the cube root function, and this is what the input looks like, x cubed. So I'm cube rooting an x cubed, and then the cube root and the third power here cancel each other out and leave me with x. In other words, taking the composition of f inverse with f of x, the f inverse and the f essentially cancel each other, leaving me with x, the input that I started with. That's symbolically saying the same thing we said kind of in an intuitive way up here. If you do the composition the other way around, f of f inverse of x, the same thing should happen. You should still end up with x, and here's sort of the argument for that. That's not unique to the cube root and the cube function. That's any function and its inverse, if such an inverse exists. In fact, that's a way of defining inverses. If a function f of x has an inverse f inverse of x, then f inverse of f of x will equal f of f inverse of x. So this is both possible combinations of, or both ways of ordering that function composition. In either case, they come out to x, the input. Okay, but again, intuitively, you want to think of an inverse function as undoing what a different function does. Now, we have a really important relationship between any particular function and its inverse when you look at their graphs. Here, the graph that's in red is the function y equals x cubed, so the one that we were calling f of x up there. The blue graph is the graph of y equals x to the 1/3 power. That's the same thing as the cube root of x. So blue graph is the cube root function, red graph is the cube function. Notice there's a symmetry about these two functions. In particular, they're reflections of each other across this green line, which is the line y equals x. And that's true of any inverse and the function that it's the inverse of. The graphs of those two functions will always be a reflection across the line y equals x. This is something you talk about in intermediate algebra, so we're not going to go into detail as to why that happens. Okay, now let's move on. So it is important to note that not every function has an inverse. In fact, a whole lot of functions do not have inverses. And there's a very important reason why. inverses only exist for functions that have a property called 1-to-1. And this is also something you talk about in intermediate algebra. And we're not going to go into a whole lecture on 1-to-1 functions because it's prerequisite stuff here. But to quickly cover the basics of it, a function f of x is called 1-to-1 if every output for that function corresponds to one and only one input. So to illustrate what I mean, the very familiar function f of x equals x squared is not a 1-to-1 function. And the reason for that is this. If I pick some output, let's just say the number 4, think of that as an output of this function. What input could be used to get plugged into this function and produce a 4? Well, I can actually think of 2 different inputs that would do that. -2 and +2. Because if I square -2, I get 4. If I square +2, I still get 4. That means that 2 different inputs are corresponding to the same output. Therefore, this function cannot be 1-to-1. Graphically, the way that we can represent that is what we're seeing right here. So this red parabola is the graph of the function y equals x squared. And here, I know it's very small, but here's 4. This is a y value of 4. So being a y value, you think of it as an output of that function. Notice that the number 4 shows up as a y coordinate of 2 different points on this parabola. And the x coordinate of each of those is -2 for this one and +2 for this one. That's graphically saying the exact same thing that I'm saying up here. So 2 different points that show up on the same horizontal line exist on that parabola, and that alone says that this function is not 1-to-1. So that gives us something that we call the horizontal line test. If you want to know whether or not a function is 1-to-1, one way of doing that is to first graph the function, and then to see if you can find any horizontal lines anywhere that hit the graph at more than one point. In this case, really any horizontal line that passes through the graph except for the x-axis will do that. Now, that doesn't mean we should give up hope, because if you think about it, the x squared function, if you didn't know this whole 1-to-1 thing, but you did know a little bit about inverses, if I were to ask you, what is the inverse of x squared? You would probably tell me that it's the square root function, based off of the discussion that we just had on the cube root and the cube function. But because the x squared function is not 1-to-1, that means that it doesn't have an inverse at all. So where is the square root of x coming from if we can't take an inverse of x squared? Well, the answer is that it actually is possible to find an inverse for a function that's not 1-to-1 by cutting it up. And what I mean by that is we impose a domain restriction on the function x squared. We artificially do this. So notice if I were to take that same function, f of x equals x squared, and if I were to restrict its domain to the interval x is greater than or equal to 0, so only non-negative values of x. All that means is that I'm cutting off all of the negative numbers from my domain, even though they would normally be in the domain of this function. If I do that, then I lose the entire left half of this parabola. And that's totally fine for what we're using this for, because notice the remaining branch of that parabola is a 1-to-1 function. It passes the horizontal line test. Any horizontal line now that passes through this graph will only ever hit this thing one time. And so this is what I can use to come up with the square root function. And we know what the square root function is. I don't need to define it, but if you notice here, the red graph, again, is y equals x squared. The blue graph is the square root function's graph. And you learn how to graph these in algebra as well. Notice, again, they're reflections of each other across that line y equals x. Okay? So this is all technically old news. Technically, none of this, like absolutely none of this, should be something you haven't heard before. But the review is really important because we're going to try and carry these ideas into the realm of trigonometry now. We've defined 6 trigonometric functions: sine, cosine, tangent, secant, cosecant, cotangent. All 6 of those have inverse functions. However, we need to do what we did with the x squared function, as we'll see in a minute, we have to impose domain restrictions to come up with those. And in this section in particular, we actually don't cover three of those inverse functions. We're not going to talk about the inverses of secant, cosecant, or cotangent. Even though they exist, we're going to restrict our attention to the three most important ones, the inverse of sine, cosine, and tangent. So let's start thinking about the sine function. If I wanted to take the inverse of the sine function, if I wanted to find an inverse function for the sine function, there's immediately a problem that we run into. Because sine is periodic, every periodic function will fail the horizontal line test. And that's because you get a repeating pattern in that graph, and any horizontal line will hit that graph in an infinite number of points, which is certainly more than one. So you can see that, you know, any horizontal line I put through my sine wave here is going to hit it in more than one place. The sine function is not one-to-one. But that's okay, because just like we did for the x squared function, I can artificially restrict the domain of this sine function so that a piece of it does pass the horizontal line test. Now, there are lots and lots of different ways you could do that. However, there is a particular interval that we tend to want to do this on by convention, where we're going to restrict our sine function to the interval negative pi over 2 to positive pi over 2. And if you notice, that's what this graph represents. This is a zoomed in version of this graph, but restricted from negative pi over 2 to positive pi over 2. The graph actually ends here and here. It doesn't continue onward, okay? We've cut off the rest of that sine function. Notice that this little branch of our sine wave, it does pass the horizontal line test. And so this thing will work if we want to come up with an inverse of that sine function. Now, like I said before, you could have cut this sine graph up into different places. Notice up here, if I made a cut here and a cut here, and then, you know, restricted my sine function to this interval, we would still have a branch that's one-to-one. But we always use the interval negative pi over 2 to pi over 2. And why is that? Well, the reason for that is because it's actually preferable to end up with an interval that contains 0. Just because 0 is a very convenient number to have around. So that's kind of really all it boils down to. And that's the interval that we're going to be using. So now that I'm restricting my sine function to this interval from negative pi over 2 to pi over 2, giving me a little piece of that graph, what are we going to do with this? Well, we're going to use it to come up with what we call the inverse sine function. Now, the inverse sine function is the inverse of the sine function, as the name implies. And we have two different notations that we use for it. Y equals... notice it's very similar to the notation that we use for a general inverse function, that -1 exponent. You need to be really, really careful. I'm going to write this off to the side. This is not the same thing as this. These are two different things. See, this one is the inverse sine function. This one is 1 over sine of x. Those are two completely different things. So it's really, really important to not confuse that -1 up there for an exponent, because even though it looks like one, that's not what it is. Okay? So inverse sine of x, this is the notation that we use for that function. Alternatively, we sometimes call it arc sine of x. And the reason for that goes back to when we defined radian measure, how we showed that the an angle subtending, an arc on the unit circle will have a radian measure equal to the length of that arc. The outputs of these functions, as we're going to see, are angles. And because those angles can be associated with arcs on a circle, the word arc makes an appearance here. You don't need to know that really for what we do in this section. It's just like a little bit of context. But you do need to know that these two things are the same function, just different notations for the same thing. So don't try to make a distinction between these two. Okay? Now again, if we go back and we look at how we cut up our graph for the sine function, I restricted my domain to the interval negative pi over 2 to positive pi over 2. What did that do to the range of that function? Well, the range of the function didn't change. It's still the range of the normal sine function. You can see that it goes as low as -1 and as high as +1. So the range is -1 to +1. Now, what happens when you take the inverse of a function that looks like this? Well, remember, you're going to be reflecting it across the line y equals x. And that causes the whole thing to kind of flip, causing the interval that I'm using for my domain to become my range, and the interval that I'm using for my range to become my domain. In other words, your domain and range trade places when you come up with an inverse function. And we're seeing that here. Here's the graph of the inverse sine function, okay? And you can see, again, this is a starting and an ending of sorts. This graph does not go beyond these points. The range now is -π/2 to +π/2, and the domain is -1 to +1. Think about that for a second. We're plugging in numbers between -1 and +1 when we're looking at our sine function. You're not going to plug in a number like pi. Okay, you can plug pi into the sine function, but it doesn't make sense to plug it into the inverse sine function because the domain is only the interval -1 to +1. We'll do plenty of examples of evaluating inverse trig functions in a little bit. We just need to derive the other two. Okay, so this kind of summarizes what I said about this down here. Summarizes what I said about domain and range. We're going to summarize all of this in a table a little bit later. But furthermore, this is the important relationship that you need to remember. If sine inverse of y, or if inverse sine of y is equal to x, then y equals sine of x. Okay, and what this does, this is basically telling you how you're supposed to evaluate inverse trig functions. You can, one way of thinking of this, think of this as like an algebraic equation. If I took the sine of both sides of this equation, we think of the sine as canceling out the inverse sine, leaving me with y. On the right-hand side, because I took sine of both sides, I would have sine of x. Okay, but that's describing that inverse relationship between these functions. Really quickly, I want to do the same thing that we did with the sine function, but for cosine and tangent. And now that we've walked through this process, we can move through it a little bit more quickly because it's essentially the same ideas at play. If you look at a cosine graph, you would actually see that it doesn't work to make the same domain restriction that we did for the sine function to come up with an inverse function. Notice this interval, if I think of this as this interval as containing angles from the unit circle, this takes us from the fourth quadrant into the first quadrant. For the cosine, both the fourth and first quadrant gives us positive cosines, and that's, if you look at the graph, it's going to cause us to fail the horizontal line test. So we have to use a different domain restriction for our cosine function. If we restrict the domain of the cosine function to the interval 0 to pi, we see that we do get a one-to-one little slice of that curve right here. For the tangent function, we want to do something similar. Remember, tangent has a bunch of these curves showing up periodically with a period of